Hello and welcome back. We'll continue looking at exponential functions in this video. So an exponential function is a function that looks like b to the x power, where b is going to be a positive number and it's not going to be the number 1. So let's look at a couple things, a couple of the properties or characteristics of the exponential function. So if we think about the domain of a function, it's all the numbers that we are allowed to plug into the function. This can be anything. We're allowed to take b to any positive number. We're allowed to take b to any negative number. We can take b to any to 0. We're allowed to plug in anything that we want into our function. The range is all the possible outputs. And one thing that you'll notice if I scroll back up to what some of the functions look like, so all of these functions remain above the x-axis. All of these functions are going to be positive forever. The range is always going to be all positive numbers. So it does not include 0. You can never get 0 from an exponential function. You can never get a negative number from an exponential function. But you can get every positive number. As these functions go up, they go up forever, so we can hit every single positive number, but no negative numbers. One other nice property is that the function always passes through the point 0, 1. And this is because if you plug 0 into an exponential function, you're going to get b to the 0 power, and b to the 0 power is always 1. So if you plug in a 0 into your function, you always get the number 1. So when we look at our functions again, all of these pass through this point right here in the middle. This point will always be passed through by an exponential function. And then there's the two different types of exponential functions. There's the ones where b is going to be bigger than 1, or the ones where b is going to be smaller than 1. The ones where b is going to be greater than 1 will look like this, where they're going to go up and to the right. Whereas functions where the base is going to be smaller than 1, the exponential function will fall and it'll come down and to the right. And then again, the bigger b is, as in the further away b is above 1, the steeper the function is going to be. Whereas here, the smaller b is, or another way of saying this, the closer b is to 0, the steeper the function is going to be. And then a couple other things is that our function passes the horizontal line test. So no matter what horizontal line you draw, our function is only ever going to hit this line in one spot. And the reason I mention this is because this means that our function has an inverse, meaning that there is another function, f inverse of x, where f inverse composed with f of x is just going to be the straight line x. So this is quite nice. Having an inverse is a very important property, and we'll discuss that inverse in the next couple of sections as well. And then the line y is equal to 0 is always going to be a horizontal asymptote. So y is equal to 0. The height y is equal to 0 is going to be the x-axis, and we can see that as our function goes, so in this case, when b is less than 1, as our function goes further and further right, it's going to become closer and closer to this to the x-axis. When our function has a base that's bigger than 1, the horizontal axis is going to be a horizontal asymptote, but it's going to be as we move further and further left, we're getting closer and closer to 0. So that's just a lot of facts about these graphs. Let's look at a couple. So we have the function f of x is equal to 3 to the x power, and we want to use that to get the graph of 3 to the x plus 1 power. I'm going to do this in a couple of ways. So let's graph, let's go 1, 2, 3, and I'll go up in threes here. So this will be 9, 6, and 3. So let's graph f of x is equal to 3x. And we know that our function is always going to pass through 1. So the y-intercept is always going to be 1. If I were to plug in a 1 into this function, 3 to the first power is always 3. 3 to the second power, 3 times 3 is going to be 9. And any beyond is going to be up and up and up. So if we think about what our function is going to look like, it's going to be something like this, where our function is going to be going up and to the right, and as we come to the left, it's going to get closer and closer to 0. So in this function up here, I've replaced x with an x plus 1. And if we think way back to chapter 2, this is going to be a horizontal shift. So we can draw the same graph, 3, 6, 9, and we'll have 1, 2, 3, 1, 2, 3. When we replace x with x plus 1, this is going to be a horizontal shift, so we're shifting it from side to side, and we're going to shift it to the left 1. So this is what happens when we add 1 to this. So we're going to shift everything to the left 1. So instead of being at height 1 at 0, if I shift it to the left 1, I'm going to be at height 1 at negative 1. Instead of being at 3 at 1, when I shift it to the left, I'm going to shift it to the left by 1. Instead of being at 9 over here, we're going to shift that to the left. So our function now looks something like this. So this is fairly straightforward. Not a lot is going on. We're just shifting our function to the left. And I do want to show one other thing, which is I want to take this function, which is 3 to the x plus 1. And when we look at this, we are adding things in the exponent. This is the same thing as taking 3 to the x power and multiplying it times 3 to the first power. So again, when we multiply exponentials, we end up adding the exponents together. So 3 to the x plus 1 is the same thing as 3 to the x times 3 to the first power. 3 to the first power is just 3. So this is going to be the same thing as 3 times 3 to the x power. And 3 times a function is the same thing as shifting it. Sorry, I shouldn't say shift. This is the same thing as a vertical stretch. So I'm taking my function and I am stretching it up by a factor of 3. And wouldn't you know it, if we're going through 1 at this point and you stretch it up by a factor of 3, it goes up to 3. We were at 3 here, and if you multiply 3 by 3, we're stretching all the way up to 9. So shifting up an exponential to the left is the same thing as multiplying it by some number. And this is just a neat aside that I wanted to show. Let's look at one other graph. Let's look at the graph of 2 to the x plus 1. So here, let's take our function f of x is equal to 2 to the x power. Let's just go up by 1s, 2, 3, 4. So we know that at 0, 2 to the 0 power is always 1. An exponential function will always cross through this point as long as it hasn't been shifted. So then at 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the negative first power is going to be 1 over 2, so it's a half, and then 1 over 4, so we've got our exponential function. And now what we'll do is we're going to add 1 to the function. And notice that I'm adding 1 to the entire function, which means that we're going to be adding 1 to the height of the function. This is going to be a vertical shift. So we're going to take the whole function and we're going to shift it up just a little bit. We're going to shift it up by 1. So from 1, we'll go to 2. From 2, we'll go to 3. From 4, we'd go to 5. From 1/2, we'd go to 1 1/2. From 1/4, we'd go to 1 1/4. And now we have our function that shifted up. Whereas before, our horizontal asymptote, maybe red will be better, our horizontal asymptote is at 0, but now since we've shifted everything up, our horizontal asymptote is going to be at 1. So our function is going to sort of flatten out right at 1 as we're going to the left. So again, we can take what we learned before about vertical shifts and horizontal shifts and draw some of these modified exponential functions. And the last thing that I want to look at is what's called the natural base, E. This is also called Euler's number. Euler being a famous mathematician from a long time ago. And this number is irrational. So this is an irrational number, meaning that its decimal expansion is infinite. It goes on forever. It doesn't repeat itself. So I can't write the whole thing down. I can't write a pattern for you to see. However, there is a way to calculate this number, and this is something that you can just plug into your calculator to see the first few steps of. If you take 1 plus 1 over n raised to the nth power, and you start plugging in bigger and bigger and bigger numbers. So if you plug in 1, so 1 plus 1 over 1, that's 2. To the first power is 2. 1 plus 1 over 2 to the second power is 2.25. If we start going up, plug in 5, you plug in 10, you plug in 100, you plug in 1,000. And what we see is that this decimal is slowly getting closer and closer and closer to this decimal up here. I'm only showing the first 4 digits beyond the decimal point, but we have to get really, really big to get this to look like this. So this 1 plus 1 over n to the nth power is something that shows up in a lot of different situations. So this is a very useful number. And if you write down the exponential function with e as the base, this is called the natural exponential function. And so for instance, f of 2 here, e squared, 2.7 blah 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 is going to be that squared is going to be about 7.389. So this is just something that you have to plug into a calculator. And most calculators come with E built in. So we can do this here, where the gray wolf population of the western Great Lakes region is modeled by this function. 1,145 times e to the 0.0325x, where x is the number of years after 1978. So it asks, what's the wolf population in the year 2017? Well, so 2017 minus 1978, well, this will be 39 years. And I can plug this into here. So f of 39 is going to be 1,145 times e to the 0.0325 times 39. And this is, so rounding to the nearest whole wolf is going to be 4.67. One thing I'll caution you on, be careful when putting this into calculators, because you'll probably want to put this in parentheses up here. the parentheses will help